Are we good?
Over to you, Florent, please.
You see my slides?
Yes.
Okay, so thank you. Surya suggested I reuse partly a talk that he saw, but I also wanted to make sure that he was not too bored. So I was trying to include new stuff. And pardon the grandiloquent title, how do neural network learn simple function with gradient descent? I wish I knew, but that's my best attempt to understand that. And it's essentially a bit of a summary of what I've been I and Lenka as well, and many others have been doing over the last 5, 6-ish years, something like this. Okay, so it's a theory talk, and and we're all happy with that. So the question is, what is the role of theory, and what is a theory? And it can serve many purposes. And I really like to start my talk with this quote from Leo Brayman, who's an amazing statistician who wrote historical pioneering papers. And he said that there are 4 use of theory: comfort, insight, innovation, and suggestions. And all of them are useful in their own right. So today, I will try to see, or my attempt to get insights, the kind of thing that make you, haha, that's why it works. And but what I'm trying to do. So I'm not trying to, propose anything new or to understand something that we know works, or to suggest new techniques, just really old stuff, but why is it working? And I also, I think for this audience, it kind of makes sense, but I really like that in the same paper, is saying that an important thing for insight is inquiry. And an inquiry is a sensible and intelligent effort to understand what's going on. And he's giving as an example, analogies and simplified models like the Ising model, which, I think we can all agree that this is something that worked well in physics. So what am I going to talk? Well, I'm following this line, and since I'm a physicist by training, I like really simple stuff. Even though studying simple stuff can be complex, and I try to focus on understanding very simple, some might say simplistic problems, right? In the same way that if I do in biology, I will probably start by a spherical cow in vacuum. When we learn solid-state physics, we basically spend all our time with harmonic oscillators and then a bunch of harmonic oscillators. So in my case, I will just look at machine learning with Gaussian data. So Gaussian data is really ridiculous in many ways, but at least I can try to do something with it and to understand what's going on. So it's a limitation, and I start with that. Of course, I will not reach AGI with this. But maybe I will reach AGI, artificial Gaussian intelligence, which is a lower bar to get. And just to give you a sneak peek, if the talk goes well in time, that's the kind of thing I want to show you at the end. A problem for which, well, you have, when you increase the number of data, you get some curve for lazy training and kernels. 2-layer net have a curve that is going lower, and 3-layer nets is going even lower, and so on and so forth. That's the kind of the thing I'm trying to get in sample models. All right, that was the intro. And let's see. So I said that I will be trying to discuss our attempts into how machine learning or neural network can learn functions, some functions on Gaussian data. And so I will start by describing these functions. So they are called multi-index functions. And I will introduce the function here and explain the problem. So here it is. So you have some data, X, and now you take this data, you multiply X as a vector by a matrix W, which is D times R. So W is an orthogonal random matrix. It projects your D-dimensional vector into R-dimensional one. So 1 or 2 or 3. R is finite. So I'm just really projecting my vector to 3 or 4 dimensional. And from this 4 dimensional, I'm applying a function and I'm returning a number. Okay, that's the definition of a multi-index function. Multi-index refers to the fact that R is 1 or 2 or 3. So just to give you a very simple example, the single index example will be, okay, I have one direction, so X is multiplied by W star. I have a number H star. And now I'm applying a function, so it could be itself. I can give you H star, that's called the linear model. Can give you the absolute value. This is sometimes called phase retrieval. Can give you the sign of H, or the sign of H plus some random noise. That's sometimes called the perceptron problem. These are all instances of this problem with R equal to 1. And I can look at problem with R is equal to 2 or 3 or 4. So I have projections with R numbers. And now my function G star is doing something to these R numbers. So for instance, I can take, H1 plus absolute value of H2, H1 plus 2H2, blah, 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 any polynomials. Or I can even do something more fun, like applying, a nonlinearity and sum them up. That's what sometimes is called a committee machine. So these are all examples of single index and multi-index functions. Okay, and so what I want to know is the following. If I prepare a data set with n Gaussian vector x, it's a completely random vector, and now I'm applying this function to x, and I get y, so I have labels, and I have a data set with x and y. I have n data, and D is very large. Can we learn this function from the data? Okay, can the machine learning techniques learn the function f from only x and y? That's a very generic question. Right, and of course, we want to know what a neural network will do on that, because that's what everybody will do. And so, for instance, I can try to fit this data with a 2-layer neural network, probably over-parameterized. So the number of neuron P will be really, really large, and so on and so forth. And, and I would like to know what will be the performance of a 2-layer net on that kind of problem. Okay, so the simplest thing to do will be to say, fine, training a layer net is too hard. I'm going to do something simpler and do lazy training. Or random feature, or kernel methods, or neural tangent kernel. All these things are kind of equivalent to essentially trying to fit with a neural network in which I'm not. I wish I could see my pointer. Let's see if I can get the pointer to work. No pointers. Okay, let's see. All right, I'll try to be very clear so that you don't need the pointer. So the lazy training approach is really like you don't train the first layer. You don't train W. You just take the first layer random, and you learn the second layer. Okay, and it's a very interesting avenue for research. A few years ago, everybody was looking into that kind of stuff. And so the first question you may ask is, okay, how good is it if you try to do something like this for learning multi-index function? And the bad news is that it's not really good. It's pretty limited. And I've wrote paper about it, and many other people did. But this paper by there is a very nice theorem by Song Mei, Theodore Mizakiewicz, and Andrea Montanari, with basically explaining what is going on if you try to do kernel fitting here or lazy training or whatever. You are essentially only able to learn a polynomial approximation of the function you're trying to fit. And polynomial what? Well, let's say that you have n data and 2-layer net of width p, and now you look how they grow. And if they grow like d to the kappa, where d is a dimension, you take the smaller of the two, and let's say you have, p is infinity and n is d square. well, then you can learn only a polynomial of degree 2. If n is order d, only a degree of order 1. So that's the situation. You know, f and p are order 1, you learn only a linear function. If it is d square, only a quadratic, d cube, only a quartic, and so on and so forth. So it's pretty bad for this problem. Essentially, kernel methods for Gaussian data or any lazy training techniques is essentially just doing a polynomial fitting, okay, which is obviously not really good. I mean, if this is what you wanted to do, you should have forget machine learning and neural network and just do a polynomial fitting. So it's pretty limited in this setting. So we have to do something. And of course, what we have to do is not to use a completely random set of features. So that's the first part of the plot I want to reach. You know, if you plot the generalization as a function of kappa, where kappa is log n over log d, for that kind of problem, with any of these kernel random feature lazy training techniques, what you get is a succession of stairs. And when n start to grow like d, you can learn the linear part. When it grow like d squared, quadratic, and so on and so forth. And that's what it can do. Okay, so of course, it cannot be the best thing ever. And in fact, if you just do one step of gradient descent, you get much better performances. It's very easy to see. Even with one step, you can observe many interesting phenomenon. For instance, you do one step with a large batch, you can see that your data are not longer like a purely random matrix. There is a long tail in the spectrum of feature covariance. That's the kind of thing that we see in deep learning all the time. And so we know that as soon as you are doing some updates, you are doing better, and you can start to feed the function better. Now, I'm going to give an argument that will be key to understand all the results in what follows. So imagine that your neural network, you have done, yeah.
On the one step of gradient descent, what are the statements you can make, and how does it depend on the nonlinearity in the ground truth data?
Okay, let me skip this.
Okay, all right.
It's a great question. But that would require, a detour. It's okay. Let me answer fast. With one step,
okay.
you can learn a lot.
I see.
Okay, but not as much as you want.
Okay.
But I will be happy to discuss this. You can check out the paper we just wrote with Yue Lu on this topic. We have a RMT approach on that.
Okay, great.
Yeah, sorry, but that's really going. Okay, so imagine that you can really learn everything. So imagine W hat is really learning very well W star. Okay, and it may not happen with only one step of gradient descent, of course. We are going to discuss what you need. So if W hat is correlating with W star, essentially you expect W hat to be something like a random matrix Z1 times W star plus a random matrix Z2. That's the kind of learning that you could expect that is going on if you have some good feature learning. Of course, W hat cannot be exactly W star because they don't even have the same dimension. And they have to be aligning up to some rotation and so on and so forth. But that's what you expect. Now, of course, if you have done something like this, if your first layer have learned a feature, if you plug this W hat into your formula for your neural net, well, you see that essentially now your neural net can be written as follow. And if now what it's doing, it's still something that looks like a random feature if you think about it, but Z1 W star X, it's what I call H star. So now if you do feature learning, you still are doing, random projection, if you want. It's still a random projection problem. It's still a random projection method, but now it's operating on H star and not on X. And that's really, really the crux of why it should work, because now you still have these polynomial problems that, you can only learn polynomials, approximation, blah, blah, blah. But not with respect to X, which is in dimension D, but with respect to H star, which is in dimension, 2 or 1 or 3. So as long as N and P are large enough, you can learn perfectly everything because you just need to be polynomial in 3. So obviously feature learning is key here, right? And the way that feature learning is operating is that you start from something which essentially would be random feature in large dimension to random feature in small dimension. So if you could learn this, if you could really learn all this stuff, that's what we would expect, right? Like suddenly, once you do feature learning, you can fit everything very well.
But Florent, there's one question in W
Yes.
hat signal to noise ratio, right? If you go back to the formula, the
which part?
So W hat is Z1 W star plus Z2.
Yeah.
You're making that as an assumption, but then you have
Yes.
to use a signal to noise ratio, and that has to
Yes.
be
For instance,
learning.
here I am assuming Z1 and Z. Look, this is an idealized scenario. Now we are going to see if this is happening. I agree. For instance, if this is happening, but Z1 is 10 minus is order 10 minus 6, and Z2 in 10 to the 6, we have a problem.
Yeah. So you have some potential control over how much data you need to get
exactly.
to
The question is for now I'm just assuming this is happening. And I'm claiming if this is happening and Z1 and Z2 are order 1, this is really, really nice. It's just random feature on H star and problem solved.
Yeah. Okay.
Now, you're right. The question is, how do you reach something like this? And something where, the Z2 are not shadowing your learning part. And so that's the question, right? We need feature learning. We really need feature learning. Otherwise, we are with lazy kernel. And so we would like to reach, that green curve. But for this, we need to have a method that is learning W star from W, right? And how are we going to do this? Well, of course, we need to understand what gradient descent is doing. Okay, let me don't do this first and cheat. So it turns out that physicists looked into that kind of problem in early 80s, late 80s, early 90s, and they entirely solved this problem in some sense, which is a completely cheated sense, but that's still instructive. So let's follow what they did. They cheated, but it's still good. So they did the following. They say, look, what if we know J star, so we know exactly the kind of function that you have been doing. We just don't know the projection. We don't know the projection matrix. We just don't know the feature. Okay, so this is a really crazy strong assumption that we should not be making. However, if even knowing what J star is, you cannot learn the W's, you're going to be in trouble. Okay, so for some reason, that was looked to death, especially among the statistical physics crew. The kind of problem we have looked first, to my knowledge, by Bernard Derrida and Elizabeth Gardner, and then many people looked at this, including some famous people that I'm quoting here. So they looked to this to death. I'm not going to tell you what they did. I'm just going to give you what is important for us. They basically show that in this case, if n is order d, you should be fine. Okay, maybe it should be 4d, 10d, 100d, something like this, but that's enough to learn entirely all the features. Okay, this is what you need. You need order d data, and then you should be fine. And recently with some of my colleagues, because we try to talk to probabilists, we actually took all this literature and proved everything with math techniques. I mean, that's information theoretic statement, but that's not very important. The important thing is with ordered data we can learn. Now, but we can learn. What I'm saying here is that it exists a method that can learn. I'm not saying the method is practical. And in fact, if you ask, what about a practical method, that is an algorithm that can learn in reasonable time, it's another question. Turns out that physicists look at this too. It's essentially, you know, some spin-glass theory again, and it followed this amazing paper by Towles, Anderson, and Palmer, who essentially wrote the mean field equation for this problem, and they iterated the mean field equation. And we know now, actually, there is some amazing work from probabilists that show that this is the best algorithm we can hope for in that run in polynomial time. So we even have the best algorithm for this, the best conjecture algorithm, because we don't know if P is equal to NP. And with this algorithm, we can classify all these set of problems and know which one you can learn and which one you cannot learn in practice. Okay, so I'm just flashing what the algorithm is, but I'm not going to tell you what it is. You know, it's just an iterative algorithm. You know, I have the data and I'm iterating them. That's why it's practical. But what it's important to realize is that essentially the problem is you write the free energy of your problem, of your estimation problem. You write it as a statistical physics problem or the field theory problem, and you do gradient descent in the free energy. That's what it is. Okay, and at some point you have some interesting phenomenon that you can study with random matrix theory. Okay, let's just assume there is a good algorithm that does this. So the good news is that then you can classify all multi-index problems into different categories. Most of them are really easy. So I call them the trivial problem, which is essentially most problem. In most problem, you know, you apply this algorithm and you can learn the feature. So for instance, you know, if the function is h to the 3 minus 3h, that's how it looks. With order d data, it works well. So I plot the error as a function of n over d, which is what physicists do. And, you know, the error goes well. As soon as you have some data, it's good. So it turns out that if you have symmetries, it's slightly harder. So for instance, if you have phase retrieval, you have a symmetry because h star could be plus or minus h star. So you have even odd symmetry. Then you have a phase transition. It's interesting. You know, you need to go to alpha is equal to 1/2, and then you can learn. You can have other type of symmetries. For instance, this problem is called the parity problem. You know, you have two directions, and you take the sign of the product, and the transition there is at pi square over 4. So we call them the easy problem. You know, you need still order d data, but there is a phase transition. And what else? Well, then there are the hard problems where this algorithm doesn't work. And basically, there are almost none of them. But if you want one, it's the favorite algorithm problem of computer science. It's called the parity problem with more than 2 directions. This is known to be one of the hardest problems in the polynomial hierarchy. And okay, that doesn't work. Okay, but as far as we know, basically nothing would work here. We don't know any polynomial algorithm that would be working. So parity with more direction is hard, right? So just to show you that it's, you know, this thing is not only physicists. If you go to a computer science department, you knock on the door and you ask them, okay, did you try to classify which of these functions are easy and which are hard? And they say, sure. We use something entirely different. It's called statistical Curry's bound. It's blah, blah, blah. And, you know, I'm not, you know, we could discuss it if you want, but that's not the point. But the interesting thing is that they found the exact same classification. Most functions are easy. You can learn them in order D set. If you have some symmetries, well, then you need order D, but there is a phase transition. And then you have those guys which are super hard. Okay, so very nice. We can apply the algorithm. It works. You see that, you know, this is for phase retrieval. This is for the 2 parities. Perfect. So the situation is that thanks to all this work, we know when it is possible or not, and we have a good idea of how much data you would need to get a good learning of these features. But this is cheating, right? Because I cannot assume I know in advance the form of the function. That's not how it works. That's not the rule of the game. I need to learn what the function is. And also, this is cheating because no one cares about TAP or AMP or any of these methods. People are doing gradient descent. So you would like to know what happened with gradient descent.
Actually,
Okay,
Florent,
so
how do you know that AMP is the best method amongst all polynomial algorithms in all
that's a very good question. So you have to be really careful with best, but you can show the following. If you define first order iteration, which is I'm receiving the matrix, I'm multiplying with a vector, and I'm doing a nonlinearity. This includes gradient descent, by the way.
I see.
Then you can show that any such first order method, you can show this through DMFT, by the way, which is interesting. It's it has been done by physics approach. Any first order algorithm can be written like this. And then you can optimize over all of them, and you will see that the best one is just TAP.
I see. It's very nice.
It is a nice result. It is a nice result.
I have a question as well. So what do you mean by the function G star, but then you are still labeling the number of data points you have? In what sense do you know the function G?
Okay, so that's a really important question. So what I mean, and I wish I could move my pointer. So my function is f star as a function of x. But I can write it as G star as a function of H star. Now, I know J star, but I don't know W star. So you know the function when it's applied to the low-dimensional subspace, but you don't know in advance the projection.
I see.
Right? And so here I'm just saying, okay, I'm just learning the projection. But of course, knowing the form of the function is really helpful.
Okay, so the committee machine would be an example of this.
Exactly.
The function
machine
G star
will be a perfect example of this.
Okay, thanks.
I mean, a matching architecture committee machine would be a perfect example, yes. Right? But of course, we don't want this. What we want to know is, okay, look, I don't know the function, and I'm not using any of these AMP, TAP, and everything. I'm just using a two-layer net, and I'm doing gradient descent. And now, if neural networks are truly that amazing, maybe they can be just as good in terms of data. They can, be able to learn these features just as well. And so that's the question I want to ask. Okay, it's a good moment for question. Okay, I go on. So it turns out there are many, many ways in which you can study gradient descent with Gaussian data. I mean, Gaussianity really, really is helpful. It comes with its own set of problems because no data is actually Gaussian, so it's ridiculous, but it is helpful. And there have been huge amount of work on trying to understand gradient descent with two-layer network with Gaussian data. The first of which, actually, to my knowledge, is by Sarah Schola and David Saad, who are actually physicists. And that's dates back to 1995, which is interesting because they were looking really at problems in which you have one data at each time. Yeah, really like online LGD, one sample at a time with a new fresh batch of data and throwing it away. And it's remarkable because at the time, I mean, of course, the paper by Monroe existed, but that was only at this time that people like Léon Boutou was trying to say, well, learning gradient descent with doing one sample at a time would be actually a good way to do it. And it's funny that they were looking into this before it became popular. So huge amount of work on the topic, and I'm not going to go through them. But the important thing is the reason why it's easy. I mean, it's easy. The reason why you can study it easily is because you are doing one sample at a time. The sample is Gaussian, and you never repeat data. All right, so I will do a bit of math, but since I don't want to do complicated stuff, I will give you the argument, what happens in this case. And again, there have been huge amount of work, some of them by probabilists, some of paper by Gérard Benarous are like 200 pages of fancy math. But the core of the argument is the one I'm going to give you, which is the following one. Imagine you do spherical gradient descent, and you learn one direction. Spherical gradient descent is essentially this iteration. W at t plus 1 is W at time t minus gamma times the gradient minus gamma square time a constant time yourself. So what I want to know is if W is aligning with W star. Okay, and that's really the important point. So let me project W to W star, to the target one. So that's what it is. And I call this M, because I'm a physicist, I think of this as a magnetization. So we have M of t plus 1 is M of t minus learning rate times the gradient times W star minus something which is order gamma squared. So when we look at this, we see it's clearly the limitation is, will the gradient align at every time? At some point, it will. If it must align with W star, and then maybe or anti-align. Maybe I will have M growing, right? Because of course I'm starting with random conditions, so M is 0. Okay, so if you average over some time, and this is where you have to be a bit more careful with the math. It's clear that this can be written as an ODE, and the derivative of magnetization is just given by the average expectation of how the gradient is correlating with the direction that you are looking at. Okay, so you have an ODE, and it's not even a very complicated one because you have to make averages over X, but guess what? X is Gaussian, so all that is easy. So we can even do it in one slide. W star X, well, this is Gaussian because X is Gaussian, and Wx is also Gaussian because X is Gaussian. So actually, you can just replace these two averages in d dimension by an average in 2 dimension, where you have H and H star, where H is W, your current estimate of the weight, times X, and H star is W star times X. Okay, and this is a joint Gaussian in 2 dimensions. Zero mean, one of the diagonal, and the covariance is M, is what we want to know, is how much W star is aligning to W. So this whole ODE is just a 2-dimensional ODE. It's written here, and then you do integration by part because I don't like the H star here. Since these are Gaussian data, you can do an expansion. Well, not polynomials, but on the Hermite basis, which is the one that makes sense for Gaussians. And the nice thing about Hermite basis is that it's all orthogonal. So this thing is just basically keeping only a term of the expansion which have the same order. So this expectation is just the sum over all power k of M times G, K, and sigma k, which are just the coefficient of, for G, the target function, and for sigma, your nonlinearity. Okay, I'm done, and now you'll see it's really interesting because, well, you start at M close to 0, so in the sum, you are going to be dominated by the lower order. So the important point is, for G, what is the lowest order which is non-zero? Let's call this L, right? So for instance, if you have a degree 4 polynomial, you will see that everything will be 0 up to degree 5, and so on and so forth. So that's the entire computation. It's really easy to do. I mean, of course, I went a bit fast, but it's really no fancy math here. And that's what is going on. If you ask, how is the learning done? Well, it's following this ODE. The derivative of the way you correlate with the teacher is just M to the power L minus 1 minus gamma M. And then depending on the value of L, well, you can solve the ODE and you will see that if L is 1, well, you are learning with N data. If L is 2, you will need d log n equal d log d steps. If L is larger, you need d to the L minus 1. Okay, so the entire thing is really like this. You take the Hermite decomposition of your teacher function, and you look what is the first non-zero value. Call this L. Well, essentially, you need d to the L minus 1 data for this to work. All right, this is terrible. This is a really, really bad news. Because let me compare what we had before and what we have now, right? With clever algorithms such as AMP and everything, we could learn almost anything with order D data. Okay, sometimes, you need alpha C times D, but, the set of functions for which you need more than order D data was like this. It's essentially the parity problems. Most functions can be learned with order D data. Now we do gradient descent, and essentially we have to do a polynomial expansion, and if the first low-degree polynomial are not there, the function is hard. So whenever, when this appeared, the people who were behind all these works, I mean Gerard, and then it was generalized to more complicated problem by my colleague here in EPFL. They basically said, well, that's it, gradient descent is not good. It's what it is. But
Florent, can you remind me, in the AMP setting, was G star known or not?
yeah,
But in the neural network setting, is G star known or not?
no,
There's a very big difference in the setting.
I
right?
agree. So that was the rationale, right? You could say, well, not knowing it, maybe it makes it so much harder for gradient descent. And that's what I thought. But that's wrong.
Oh, okay.
That's wrong. You are going, let me now make the revenge of gradient descent.
You could do neural network gradient descent where G star is known, but that's
yes,
the old...
but you see, if you could,
Yeah.
you could, but I'm going to show that you don't need to.
Okay.
Which is remarkable. So, and that's something that I want to stress, because a large part of the mathematical analysis on gradient descent was done following that kind of problem where you were having a fresh sample at a time and you have never any repetition. Now, I know why, because it's practical, but in reality, you don't have to do this. Sometimes you go twice over the data, or 3 times, or 4 times. You do multi-epoch. And I mean, maybe just doing multi-epoch solves your problem. And the actual answer is that yes, it does. So for instance, here are 2 examples in which I take a big batch of data and I'm doing 2, 3, 4 iterations over a big chunk of data. And suddenly all these problems disappear. For instance, if you try to learn the Hermite 3 function, which will require d-squared data according to this approach, and it does require d-squared data if you don't repeat anything. Well, once you repeat, you can learn only 2 steps of gradient descent if you have a batch data. So repetition is really changing everything. Okay, so again, that's something we did with dynamical mean field theory, but I want to give you a simpler argument why repetition helps, that maybe we can often understand. And what I'm claiming is essentially that once you allow for repetition, gradient descent is actually almost as good as AMP, even though it doesn't know the function, which is really remarkable. Okay, so here is a very simple way to understand what's going on. So first of all, in most, even, so when I present this, some people tell me, well, when you train LLM, you see only data once. Fair enough, but come on, the same data is going to be there many times in your training set. There is a lot of repetition and duplicates. So you never see data once, and this is Cypher 100, and you can see exact duplicates in Cypher 100. So,
Ron, this will warm your heart. We were looking at deduplication in CLIP, and we found the EU flag appearing like a million times in the data set.
So look, what we did was to try to do the simplest setting. We still do one batch at a time. Okay, I'm receiving one data, I'm doing gradient and I throw it away. But here is the catch. When I receive my data, I do 2 steps of gradient and then I throw it away. These algorithms are called extra gradients algorithm. There are many of them actually around. And it's enough. Basically, what you can prove is that with extra gradient algorithm, you can do learning really, really well. I'm going to show you the result, but let's try to see why is it true mathematically. So you remember that was where we were. Okay, but now I'm doing 2 steps. So what is inside the sigma here is not the gradient at time t, but the gradient at time t after one update, right? Because I'm doing 2 steps of gradient descent. And now there is a big change, because if I write all this as a function of my Gaussian field, I don't have a clean separation as before, because before I had only h inside sigma prime. Now I have both h and h star. So the formula is much more complicated. And if I try to repeat this trick of projecting into polynomials and everything, I have something like that, which is much more complicated. And in particular, you see that what I'm doing with respect to before, this big parenthesis before, that was something that was just h. Now it's something which is itself a complicated transformation of y. So when I do see data twice, it's like I'm transforming my function and in a complicated way. And so that kind of cancellation that we had before is completely destroyed by repetition. Every time you do repetition, all this cancellation we had before cannot occur. And you know, it's actually interesting, because that's something that was known in computer science, that the power that you get by asking questions to a data set of the form expectation of y times transformation of the data is much lower, much less powerful than applying transformation both to y and z. And you know, essentially, once you do that, you can show that you are learning everything. So here is the result. You can learn any of the trivial direction that AMP was learning. You can learn the features very well to very good signal-to-noise ratio with order D data. And this direction that required at least, you know, alpha times D, alpha C times D, well, okay, I need D log D. But what's a log between friends? And okay, the hard one, they are still hard. But what is remarkable is that a neural network, over-parameterized with gradient descent, if you have repetition allowed, will be able to do feature learning with, you know, order D log D data, which is basically as good as the best Bayesian method that we have, you know, we work 40 years over, while those stuff are just off the shelf. So I was really, really impressed. And essentially, yeah, that's really what is going on in this problem. If you are trying to learn a multi-index model, and if you have, you know, a number of data that is growing larger than D to the, you know, D log D or D to the power 1.1, you know, that's what you expect. You are going to have your neural network learning the features that allows the projection in low-dimensional space, and then you can learn everything. And you know, the moral of the story, which I was really surprised, is, you know, two-layer net are essentially extremely efficient in learning multi-index models. Even though they don't know the function, and they have to learn both the function and the projection. So that was something that I thought really, really interesting. So let me just, you know, show you something a little bit more exciting, because some of this is nice.
I had a question. Like,
Yes.
let's say you go through all the samples once, right? And
Yeah.
then go through the same set of samples again. So now there's a very long distance in time between the
Yes.
first sample and the second. Your methods will not generalize to analyzing that, but what's the performance of that relative to what you
It
did?
works just fine.
I see.
And I have no idea why.
Is it better or worse than the
Okay, that I don't know. I have to look, but in the sense that it's good.
I see. So
But I
somehow
know it's good.
the memory of a training example from one epoch ago completely changes the fresh sample analysis.
Yes, and apparently, this thing retains memory over a very long time.
Yeah.
So you take a batch, data order D, you do this. I mean, we did a simulation, it's crazy. You do this, no learning.
Yeah.
You do second step, and so that I'm really surprised. And you cannot really analyze it with this technique. I guess you could analyze it with, DMFT or, that kind of techniques. But that I found very interesting, that memory can be written on long time like this.
Yeah, it's very
And I don't understand it.
Okay. Interesting. So two epochs is very different from one epoch.
Yeah,
Or
can you believe it?
two epochs is very different from one epoch with double the amount of data.
Yeah, yeah. I'm still, I still don't believe it, but it is
Interesting.
Okay. Let me discuss one last thing, which I think is interesting. So one of the bad side of what I'm showing is that in some ways multi-index functions are boring. You can learn them with two-layer nets. Okay, but what we want to understand is why deep learning works. So we would like to see something on which there is an advantage to use 3-layer nets and 4-layer net and 5-layer net and so on and so forth. And so that's one of the things we have been working over the last 6 months a lot. And that's a very short preview of what we are doing, but I thought it's interesting in this context. So we call this the might functions, multi-index Gaussian hierarchical targets. And this is the simplest example. So you start with X. You are still projecting X into a lower dimensional space, but this time the space is big. It's not 7. It's a space in dimension d to the epsilon. Think epsilon 1/2. So it's like multi-index, but you have square root of the directions. Okay. Now what I'm doing is I'm applying a nonlinear transformation on Z, like a polynomial, pk, and I'm projecting it finally to dimension 1. Okay, so the function is written here, and you can see it immediately. It's a bit harder. First of all, there is this nonlinear pk in the middle, and also there is a really large number of directions this time. It's not like 3 directions, square root of d, or d to the epsilon. So what happens if you try to learn this function? Well, if you use kernel, not much. You are still going to do your, these are still Gaussian data, so you still have this staircase where, d squared, d cubed, and so on and so forth, where you're just doing polynomial fitting. Okay, so let's now do to what happened, now we need. So unfortunately, this is the hardest part. It's not hard, but it's a bit tedious. What happens if you train this with a 2-layer net? Okay, so let's assume that I convinced you that gradient descent is good. So let's assume that gradient descent is really efficient. Look, W star is essentially a matrix which is d times d to the epsilon. So it has d to the 1 plus epsilon data. So we could expect, if gradient descent is that good, that W1 hat will learn reasonably well W star with d to the 1 plus epsilon data. In which case, I can do like before. I write W1 hat as Z1, Z star plus Z2. And, well, then I can do the same trick. And you see that now what happens is that I'm doing gradient descent, random features, but not on X, but on Z star, the projected value. okay? This is good because now it's like fitting that function, not this function, that function. It's still a complicated function, but now doing random feature on this, I'm doing random feature in dimension d to the epsilon, so let's say square root of d. So I have access to a much better precision with the same amount of data. Okay, so you have dimensionality reduction from dimension d to square root of d. And that's already really good. And essentially, you expect something like this. You know, once you start to learn z, you know, you have a random feature now in z star, so you have better thing. And every time you add some chunk of data of dimension d to the epsilon, you are fitting polynomials of the function dimension of z star. So this, you know, is a dimensionality reduction, which is really efficient, and that's how two-layer net are outperforming one-layer net here. Of course, two-layer net are not a magic bullet because the function on the right here is still complicated and non-linear and everything and so on and so forth. So you still need a large amount of data to fit it. Now, on the same example, you can ask, okay, what happens if I do a three-layer net? So you can play the same game. Your first layer, W1 hat, will learn W star with d to the 1 plus epsilon data. So after d to the 1 plus epsilon data, you are essentially doing, you know, random feature in dimension of z star. But now you should expect that W2 can try to fit what is inside the function, because what is inside the function is a polynomial of degree k of z star. And so if I have enough data, with W2 sigma, I should be able to learn to fit the polynomials. And gradient descent should be able to do this. So if I have d to the k epsilon 1, because these are the number of you know, unknown in my polynomial, I should be able to learn the polynomial. But in that case, now my three-layer net is doing random feature, but directly on H. And what I have done here is to go from dimensionality reduction from d to square root of d, or d to the epsilon, and a three-layer net go then further to dimension 1. And that's what you expect, essentially. So now I arrived to what I wanted to show you. You have an advantage of depth for that kind of function, and you can show that three-layer net outperform two-layer ones by this mechanism of dimensionality reduction. And so, you know, now of course this is like, oh yeah, if you can learn and everything, but you know, we can prove it using these techniques. So you know, I'm just flashing the theorem, but the theorem is basically telling you that what I'm explaining is what is going on. That you have really this thing that the first layer is learning, you know, the first layer of the teacher, the second layer is trying to fit the polynomials, and then you have dimensionality reduction, and you have the advantage of depth, which is kind of remarkable. Of course, you know, we have to make assumptions. We cannot do really gradient descent, so we are doing a layer-wise procedure. We are first learning W1 hat, then learning W2 hat, and then learning W3 hat, you know, because doing backprop is a bit too hard mathematically, but you know, that's still something that we could do. And we can generalize this to, you know, essentially any depth. I mean, it depends if you want me to be rigorous or not, but with physics techniques we can. And we can show, for instance, that if you have a three-layer function, like, you know, this one, where you know, you're trying to learn a function that is operating, you know, so this function is going from x multiplied by W1, then you go to something, sorry, that is in dimension, so the function is on the right, you know, you go from x in dimension d, then boom, you go to h in dimension d to epsilon 1, then you have some kind of tree-like structure. We have to use that kind of hierarchical tree-like structure to be able to do to handle the function. You go to dimension d epsilon 2, and so on and so forth. So here you have, you know, a hierarchical target. Well, what is going on is that W1 will learn W star. At this point, your neural network will be operating on dimension d epsilon 1. Then W2 will learn the polynomials that goes from H1 to H2, and so on and so forth. And every time, because of depth, you are going to work on lower and lower dimensions. So it's really something like coarse graining, and depth is really like a small filter that distills data to lower dimensional representation. It's a bit, if you think every time you are renormalizing to go to a different space with lower dimensionality. So every time you learn, you are still dominated by polynomials fitting, because that's what happens with the last layers. But that's okay, because it's polynomial in lower and lower and lower space. So just to finish, just flashing this example, let's say you want to learn this function. So you start from x, you multiply by w star, and then you have h1. Then you apply a polynomial on h1, and you multiply by a2, something complicated, then give you h2. Then you type from h2, you apply a polynomial, and you multiply by a star, and you have one number. Okay, so that's a complicated target. So if you try to learn that with a 3-layer net, that's what is happening. With n to the 1 plus epsilon data, you can learn h1, because you can learn w star. And so then that means you go from dimension d to dimension d to the epsilon 1. Then, to go from h1 to h2, it's complicated, because you have essentially d to the epsilon 2 polynomials, each of them with d to the k epsilon 1 data, where k is a polynomial you applied. But let's say that you have d to the k epsilon 1 plus epsilon 2 data. Then you are learning h2, and then you're basically doing random feature, but in dimension h2. And if you are learning then the part that goes from h2 to h3, then you are doing random feature in dimension 1, and then you are doing perfect learning. And so that's what we are investigating now. I'm trying to finish writing the paper on this. But I find it a really cool example where we can show that gradient descent can actually learn representation, and it's better to use deep neural net than shallow ones. And there are many papers that show that you can do better with deep network, but they are either linear network, or they are using they are not constructive. They are saying it exists something, but the trick is to show with gradient descent, which is what we do now. So okay, but that was just to flash what we have been doing recently. So that's it. I'm done. Conclusion perspective. So 2-layer net can learn random multi-index function. Interestingly, you can generalize multi-index function to hierarchical version of them, and then you can show that there is an advantage of using deep neural net, and this advantage goes with some learning of features that goes to lower and lower dimensional representation, which I find very nice. And now these are interesting tools that we have spent time to develop, and so there are many things I want to do with this. Of course, looking at more realistic data and architecture, and we've been trying to look into a mixture of Gaussians. There is a very nice paper that Lenka did recently, where she showed that you can actually model transformers and some sequence model with that kind of multi-index approach, and using convnets and symmetries and so on and so forth. Another thing that I have in mind is to try to generalize these functions such that instead to have these brutal stairs, which is not very realistic, it would be nice to be able to derive scaling laws. And I think we could do this. It's a bit of work. And everything I show was trying to see how we can understand generalization problems, advantage of depth and everything. But of course, there are other things you can do, and investing in adversarial attacks and robustness, a generative model, or uncertainty classification, and that's some of the other stuff that are on my mind right now. And these are the kind of things that keep us busy at night. Okay, I think I'm done in time, and let me thank everybody that ever was in my group and Lenka's group over the last 10 years, and most of them are here, and so thanks to them, they did the hard work.
Great, thanks.
This is Krzakala, by the way, Surya, in case you
Yeah, I saw your email. Have to get permission. Yeah, it's a great talk. I had a question about the last part where the target function had progressive reduction in dimensionality.
yes.
There's other settings like sparse, overcomplete, representations, dictionary learning, and so forth, where there might be an increase in dimensionality
Yeah.
target function. And so then this argument for efficiency breaks down there, but does it actually break down in practice?
So I don't know. Look, okay. Let me say it. Let me say it this way. What I was looking for is something on which multi-layer net has an advantage.
Yeah,
Now,
that's
dictionary learning, you're not doing multi-layer net, right? You're doing something quite clever. You're really trying to identify patches. You are putting sparsity in it and everything. And, you know, so I'm a bit cheating again because I'm designing functions where I can show something.
yeah.
Right? So now the question is, you know, is it even reasonable to assume that this function have anything to do with anything real? I would say it's not crazy to think that many problems have a structure like this one. I mean, you know, think about it and just think, well, you know, you go there, and then you have some kind of tree legs construction. You know, think of wavelet decomposition for images, or the kind of thing that Mathieu and you know and Francesco have been doing when they do trees for tree modeling for language and everything. Yeah, it's not completely insane. Now, is this realistic? I don't know. And you know, are other methods, you know, also able to show some advantage here? I don't know. I mean, that's you know, what I can say is that at least it's something on which I can study gradient descent multi-layer with non-linearities and show, you know, with you know, mathematical techniques, or actually for the multi-layer, it's really just statistical physics techniques, an advantage of depth. And I was pretty happy about this, right? I mean, of course, it's not so surprising because we know deep learning is good, but you know, it was not so easy to come out with this. I mean, you know, it was hard enough to show that you are beating kernel. So
yeah, no, this is very nice.
Besides, sorry, if I ask another question, maybe a little technical on this. In principle, I guess when you're the network you choose to learn this kind of representations with GD, it will have in principle lots of neurons, even in the intermediate layers, right? So you could accommodate eventually whatever kind of like more complex function as you go further down in the hierarchy. This is just the spatial part, if you wish, that has to be coarse-grained.
yes, but wait, my neural nets are immensely more powerful than the target.
Yeah.
Right? I mean, I'm trying to show this in this plot. You could see that the neural network is wider. You know, and it actually, you need overparametrization, otherwise gradient descent will kind of fail here. But yeah, I agree with you. I mean, you know, it's just some example. But in many ways, I was looking for example because multi-index functions were too easy. So, you know, but come on, I mean, this plot looks a bit like some of the plot, you know, you guys have been doing on language models. So yeah, it's not crazy to assume like tree-like structure when you do patch of data and you do stuff like this.
Yeah, of course. I'm completely on board, of course, on this on this view.
I mean, the reason I do it this way is for mathematical reason, by the way, right? If you look, why do I have a tree structure like this? Because I want my data essentially to be Gaussian and not correlated at each, you know, at some point at each stage, and so I need to do that kind of that kind of stuff. But you know, I think you know, also the reality is that I would also like to have X itself not being Gaussian and having a structure that correlates with what is being learned. You know, there are all sorts of limitations to these approaches. But still, you know, like I found it's cute that there is this thing, and you know, you have this. I mean, I think it's very intuitive, and there is nothing particularly surprising. But the difficulty was to actually show that it happens with gradient descent, and that, you know, there is actually some learning. So that's what took us some time here.
Yeah, look forward for when it's coming out on publicly, I guess.
I'm trying hard. But Surya is asking me to fill some forms until tomorrow. So, yeah.
Please do. I'm trying to get you some money.